Hey everybody, and welcome to another lecture in probability. We're going to build on the very last example of the previous lecture. Today we're going to be talking about independent and dependent events. And the last example, or the last two examples of the previous lecture, illustrate this concept perfectly. Let's define independent. Two events or outcomes, E1 and E2, are independent exactly when the occurrence of one does not alter the probability of the other occurring. Two events are independent exactly when the occurrence of one does not alter the probability of the other occurring. And we could even generalize this a little bit more and say the events are independent exactly when the occurrence or non-occurrence of an event does not alter the probability of the other occurring. And the example that we had toward the end of the last lecture illustrates this perfectly. A card is drawn from a shuffled deck. Now, what does it mean if the deck is shuffled? Theoretically, it means that every single card in that deck is equally likely to be chosen. Any of the 52 cards is equally likely to be the one that's chosen. A card is drawn from a shuffled deck, it's observed, and it's returned to the deck. And after we return the card to the deck is reshuffled. And then a card is drawn from the deck again and observed. Now here's the point. When we take the first card that we draw and observe it and return it to the deck, and then we shuffle that deck before we select the second card, that first card that we drew is just as likely to be selected on the second draw as any other card in that deck. So if we've returned the first card to the deck and the deck is reshuffled, then every card in the deck theoretically is equally likely to be the card that we draw the second time. And in this example, E1 is the event or the outcome that the first card drawn is an ace. And the probability of that happening, the number of outcomes that result in E1, that is the number of outcomes that result in an ace being drawn, over the total number of outcomes, 4 over 52. We take this card, return it to the deck, reshuffle the deck, and draw another card from the deck. E2 is the event or the outcome that the second card drawn is also an ace. But how many of those equally likely outcomes will result in an ace? There are still 4 cards in the deck that are aces, all equally likely as any other card in the deck to be drawn. Whoops, this should say E2, I beg your pardon. Number of outcomes resulting in E2 getting an ace the second time we draw. 4 outcomes will give us an ace. Ace of clubs, ace of diamonds, ace of hearts, ace of spades. And the total number of outcomes is still 52. Now here's the point. The fact that we may have drawn an ace the first time in no way affects the probability of getting an ace the second time. suppose E1 occurs. That is, we do get an ace on the first draw. We put it back in the deck, we reshuffle the deck, and we select another card. The probability that we get an ace on the second draw, 4 out of 52. Now, suppose that not E1 occurs. In other words, we take that first card from the deck, and it's not an ace. But we observe what that card is, we return it to the deck, and we reshuffle the deck. What's the probability that E2 occurs? What's the probability that that second card that we select is an ace? Well, there's still 4 aces in the deck, and all 4 aces are as equally likely to be chosen as any other card in the deck. So there are 4 equally likely outcomes that result in an ace. The total number of equally likely outcomes is 52. So if the first card that we the first card that we draw is not an ace, the probability of getting an ace on the second draw is still 4 out of 52. If we draw an ace on the first draw, the probability that the second draw gives us an ace, 4 out of 52. If we don't draw an ace on the first draw, we draw something else, the probability that we draw an ace on the second draw, still 452. Well, what does this all mean? The occurrence or the non-occurrence of E1 does not affect the outcome. It does not affect the probability that E2 occurs. If E1 occurs, the probability that E2 occurs is 4 out of 52. In other words, if the first card is an ace, the probability that the second card is an ace is 452. If the first card is not an ace, the probability that the second card being an ace is still 452. So the occurrence or non-occurrence of E1 does not alter the probability of E2. Getting an ace or not getting an ace on the first draw does not affect the probability of getting an ace on the second draw. And here's the point. Therefore, E1 and E2 are independent E1 and E2 are independent events. getting an getting an ace on the first draw in no way alters the probability that we get an ace on the second draw. Not getting an ace on the first draw in no way alters the probability that we get an ace on the second draw. The probability of getting an ace on the second draw is 4 out of 52, regardless of what happens on the first draw. So E1 and E2 are independent events or independent outcomes. Now let's contrast that with the very last example of the previous lecture. Here's the variation of the previous example that's really going to drive home the concept of independence and dependence. A card is drawn from a shuffled deck. It's observed, but it is not returned to the deck. So some things are going to change here. Suppose that E1 occurs. Suppose that E1 occurs. In other words, we draw a card from the deck and that card is an ace. We don't put the card back in the deck. We take that card, we stick it in our pocket. We reshuffle the deck, and from the remaining cards of the deck, we select a second card. What's the probability that E2 occurs? Well, we take the number of outcomes that result in E2, an ace on the second draw, over the total number of outcomes E2 is the event that we get an ace on the second draw. And we're assuming that E1 has occurred. In other words, we're assuming that the first card that we drew was an ace. And we took that card, and instead of returning it to the deck, we put it in our pocket. So when we select the second card, that first card that we drew is not in the deck. So if that first card that we drew, an ace, is not in the deck, how many aces are left in the deck when we select that second card? There's only 3 of them, right? So now there's only 3 outcomes that result in E2, an ace on the second draw. Now, is that the only way in which we've changed things? No. That first card that we drew and put in our pocket was one of the 52 cards that was in the deck originally. And we didn't replace that card in the deck. So after we drew that first card, which was an ace, and put it in our pocket, how many cards total were left in the deck? It wasn't 52, was it? It was 51. So when we select that second card, if it turns out to be an ace, there's 3 outcomes that will result in it being an ace, out of a total of not 52 outcomes, but 51 outcomes. So if E1 occurs, in other words, if we draw an ace on the first draw, the probability of E2 getting an ace on the second draw is 3 out of 51. Now we did all this under the supposition that E1 occurred. We supposed that we got an ace on the first draw, but suppose that we didn't. Suppose not E1 occurs, or that E1 does not occur. In other words, we don't get an ace on the first draw. What's that going to do to the probability of getting an ace on the second draw? E2 is the event that we get an ace on the second draw. The probability is going to be number of outcomes resulting in E2 over total number of outcomes we selected a card from the deck and didn't return it. That card was not an ace. So after we take that first card, look at it, put it in our pocket, how many aces are left in the deck? 4. Because the first card that we selected was not an ace. So there are still 4 ways that we can draw an ace on the second draw. Now, what about the total number of outcomes? We took that first card that we drew and we didn't return it to the deck. We looked at it, we put it in our shirt pocket. So when we draw the second card, there's only how many outcomes? Only 51 outcomes, right? There's only 51 cards left in the deck. Son of a gun. If E1 occurs, if we do get an ace on the first draw, the probability that we get an ace on the second draw is 3 out of 51. But if E1 does not occur, in other words, if we don't get an ace on the first draw, the probability that we get an ace on the second draw is 4 out of 51. What can we say about that? How would I say that? Let me see. The occurrence or non-occurrence of E1 alters the probability of E2 occurring. E1 and E2 are dependent events or outcomes. The value of the probability of E2 occurring, the probability of getting an ace on the second draw, changes depending on whether we got an ace on the first draw. If we get an ace on the first draw, the probability of getting an ace on the second is 3 out of 51. If we don't get an ace on the first draw, the probability that we get an ace on the second draw is 4 out of 51. So the probability of E2 occurring depends on whether E1 has occurred or not. The value of one of these, the value of the probability of this outcome depends on whether the other outcome has occurred or not. These outcomes or events are dependent. And this occurs often enough in probability that we have a special type of notation that we use when we're dealing with dependent events. Let's attach a name to what just happened. In the previous example, the occurrence or non-occurrence of E1 altered the probability of E2 occurring. If E1 occurred, the probability of E2 occurring was 3 over 51. If E1 did not occur, the probability of E2 occurring was 4 over 51. So here's a definition that describes what just happened. The events E1 and E2 are dependent exactly when the occurrence or non-occurrence of one event alters the probability of the other event occurring. And that was definitely the case in our example. If E1 occurred, the probability of E2 occurring was 3 over 51. If E2 did not occur, non-occurrence, the probability of E2 occurring was 4 over 51. So in the previous example, E1 and E2 were dependent events. And I'm going to derive, no, I'm not going to derive it, but I'm going to write down some notation now that we can use when we're dealing with probabilities of dependent events. Here's the notation that I need to introduce right here. Let E1 and E2 be outcomes or events of an experiment. This notation represents the probability of E2 given E1. When we see this, we think the probability of E2 given E1. Now, what does that mean? The probability of E2 given E1 is the probability that E2 will occur given that E1 has occurred. It can also mean the probability that E2 will occur given that E1 will occur. I don't think we're going to see this interpretation in our class. In this class, as far as I know, whenever we see this notation, the probability of E2 given E1, it's going to mean the probability that E2 will occur given that E1 has occurred. And the notation is important because we have some formulas involving and problems where we need to use this notation. I have a confession to make. What I told you in the last lecture is true, but it's not true all the time. And here's where we distinguish those times when it is true and those times when it isn't true and we have to use some other formula. In the previous lecture, we had the formula, the probability that E1 and E2 happen is equal to the probability that E1 happens times the probability that E2 happens. And that's true provided that E1 and E2 are independent. If the outcome of E1 does not affect the outcome of E2 and the outcome of E2 doesn't affect the outcome of E1, this formula works. this formula is only valid when E1 and E2 are independent. So that's something I need to emphasize now. Did we misuse this formula in the last lecture? No. It turns out that when we used this formula, the events were independent. For example, the first example was we tossed a coin and we tossed a single die. And we want to know the probability of getting heads on the coin and 5 on the roll of the die. Well, does the outcome of the coin tossing have any effect on the probability of what the roll of the die will be? No. Does whatever we get rolling the die have any effect on what the outcome of tossing the coin is going to be? No. These two things, getting heads on the coin and getting a 5 on the die, are independent. What happens to the coin in no way affects what happens to the die. What happens to the die in no way affects what happens to the coin. So these two things are independent, and we were absolutely right to use the formula that the probability of getting H and 5 is equal to the probability of getting H, heads, times the probability of getting 5, tails. So we were justified in using this formula because the events were independent. I just hadn't said anything about independence at that time. But now that we're talking about independence and dependence, it's nice to go back and look at this thing in retrospect. This formula works, but only when the outcomes or events are independent. This formula works, but E1 and E2 have to be independent events. Let's do a retrospective of another example that we did in yesterday's lecture. Here's another example that we did last lecture. We took a single die and we tossed it twice. And event A was that we got a 6 on the first toss. Event B was that we got greater than a 4 on the second toss. And we computed the probability of both of these happening. Probability that A occurs and B occurs. And we used the formula, probability of A and B equals probability of A times probability of B. Were we justified in using that formula? Remember, this formula is exactly the same as this formula, where A is our E1 and B is our E2. Same formula. And this formula requires that the events E1 and E2 be independent. So here, this formula requires that A and B be independent. A is the event that we get a 6 on the first toss. B is the event that we get something greater than a 4 on the second toss. Are those two events independent? If I get a 6 on the first toss, does that in any way affect what I get on the second toss or vice versa? No. What I get on the second toss has absolutely nothing to do with what I got on the first toss. These two events are independent. So we were justified in using this formula. We were justified because these two events were independent. Let's take a quick peek at another exercise we did in the lecture yesterday. Last night, or the last lecture rather, we did a single card drawn from a deck, observed, and returned to the deck. The cards are drawn with replacement. So a single card is drawn from a deck, it's observed and returned to the deck. The deck is well shuffled. So all 52 cards are in the deck, and each card is equally likely to be selected. A second card is drawn from the deck and observed. A1 is the event that we got an ace on the first draw. Ace of 2 is the event that we got an ace on the second draw. And we computed the probability that we got two aces, an ace on the first draw and an ace on the second draw. And we said that that was just the probability of A1 times the probability of A2. The probability of getting an ace on the first draw times the probability of getting an ace on the second draw. Now, this formula assumes, as does this formula up here, that the events are independent. Are A1 and A2 independent? We select a card on the first draw and it's an ace. And before we draw the second card, we put the first card back in the deck and reshuffle it. The exercise says the deck is well shuffled so that no one card in the deck is more likely to be drawn on the second draw than any other card. So no matter what we get on the first draw, the probability of getting an ace on the second draw is going to be 4 over 52. So what happens on the first draw in no way affects the outcome of the second draw because the deck is well shuffled in between. And so again, yesterday when we used this formula, we were right because the events were independent. Now, the last exercise that we did in the previous lecture may at first seem to be problematic. We might be thinking back in retrospect and saying, did we actually do that right? Let's take a look at what we did yesterday. And this is going to serve as a wonderful example for what we're talking about right now. In the very last example from yesterday, we said a single card is drawn from a deck, observed, but is not returned to the deck. Instead, we take it, we put it in our shirt pocket. The deck is well shuffled, and then a second card is drawn from the deck and observed. And we'll call the first event an ace on the first draw. We'll call that A1. And the second event, an ace on the second draw, we'll call that A2. And we said that probability of A1 and A2 occurring is the probability that A1 occurs times the probability that A2 occurs. And we said probability that A1 occurs, total number of outcomes resulting in A1 over a total number of outcomes, period. There are 4 ways we can get an ace over 52 outcomes. That sounds good. So the probability of A1 occurring was 4 over 52. And then we said, okay, Well, if we have an ace on the first draw, then when we make the second draw, the number of outcomes resulting in A2 are going to be 3, because we took one of the aces from the deck and we put it in our shirt pocket. So there's only 3 aces left in the deck. There's only 3 ways or 3 outcomes that result in an ace. And the total number of outcomes, 51, because that first card that we drew, we didn't put it back in the deck, we put it in our shirt pocket. So the probability that we got A2, according to the way we operated in the last lecture, we said it's 3 out of 51. And what is this? 1 over 13 times 1 over 17. And what was that? 1 over 221 maybe? Oh my goodness, don't make me do this again. Yeah, 1 over 221. Now, this is correct, but if our mathematical conscience is bothering us, we're justified. Because this formula assumes that A1 and A2 are independent events, but they're not. So why did this formula work? Well, what we did was correct. It was our notation that wasn't correct, because in the last lecture, we didn't know what a conditional probability was. We didn't know what the probability of A2 given A1 was. Since A1 and A2 are clearly not independent, the probability of A2 occurring depends on whether A1 occurs or not. So what we should have here, we shouldn't have this, no. What we should have here is the probability of A2 given A1. Well, why did the answer come out right? Because what we computed down here was not really the probability that A2 occurred. We used this notation because in the last lecture we didn't know this notation. But what this notation really was the probability that A2 occurs given A1. That's what that probability is. The probability of A2 given A1. And can we see that? Tell you what. Now we'll be able to see it. Probability of A2 given A1. This is what we actually computed. Because when we said there are only 3 ways that we can draw an ace on the second draw, we were saying that because we were assuming that A1 had already happened. When we said that there were only 3 ways that we could get an ace on the second draw, we were assuming that we had already gotten an ace on the first draw. And we were also assuming that we took that first card and put it in our shirt pocket, so that when we drew the second card, there were only 51 cards in the deck. What we did yesterday or in the previous lecture was absolutely right. The notation wasn't quite right because we didn't know this notation. That we didn't know the notation for a conditional probability. But the formula that we did use in actuality was the probability that A1 occurred times the probability that A2 occurred, given that A1 had already occurred. Now, let's do some more conditional probabilities. And when I say conditional probabilities, I mean probabilities that look like this. Conditional probabilities, we're going to do more exercises that look like this. We're going to do some dice problems having to do with the sum of the numbers on the two dice, the sum of the numbers on the two dice given that the total is a certain number. The premise is that we toss a pair of dice. This is exactly the same thing as tossing a single die twice. And we make a distinction between the first die and the second die. If the first, these are the numbers that we get on the first die. If the first die is a 1, the second die can be a 1, a 2, a 3, a 4, a 5, a 6. If the first die is a 1 and the second die is a 3, the roll is a 4. If the first die is a 1 and the second die is a 6, the total is a 7. The numbers in this row represent what we get if the first die tossed is a 3. If the first die tossed is a 3 and the second die tossed is a 4, row 3, column 4, we get a 7. If the first die tossed is a 3 and the second die tossed is a 5, row 3, column 5, we get an 8. First die is a 5, second die is a 2, we get a 7, and so on and so forth. With a pair of dice being tossed, this is probably a better way to represent the sample space than drawing a tree. If we draw a tree, we're going to have 36 different nodes, and it can get really complicated. Or maybe I should say we'll have 36 different branch tips. We may not be able to fit them all in this space. So with experiments involving dice, this is probably the best way to draw the sample space if we're tossing a pair of dice. Okay, here's a good exercise. Determine the probability that the sum of the two dice totals 6. Okay, well, let's see. Here's one, here's another, here's another, here's another, here's another. How many was that? Let's see. 1, 2, 3, 4, 5. So the number of outcomes that result in a 6 is 5. And how many outcomes total? We have 6 rows and 6 columns. So that's 36 different outcomes. The probability that the sum of the dice totals 6 is 5 out of 36. Okay, this is a little bit more complicated. Determine the probability that the sum of the dice totals 6, given that the first die is an even number. So we'll let E2 be the event that the sum is a 6. And E1, first die is an even number. Okay. Probability of E2 given E1 and that's going to be number of outcomes resulting in E2 given that E1 is true, and that is number of outcomes given an number of outcomes yielding a 6 given sum is 2. Over total number of outcomes given that E1 is true. That is total number of outcomes where the first die given that the first die is even. Now let me make sure I wrote that the way I wanted. The number of outcomes yielding E2, the sum is 6. Given E1, the first die is even. Number of outcomes yielding 6, given first die even. Okay. Number of outcomes giving us a sum of 6, given that the first die is even. Here the first die is odd, so nothing in this row works. Here the first die is even, and we get a roll of 6. There's 1. Here the first die is odd, nothing in this row will work. Here the first die is even, and we get 6 on the first. Let's see. No, here the first die is even and the sum is 6. Here the first die is even, the sum is 6. This row won't work because the first die is odd. This row, the first die is even. But do any of these sums equal 6? No. So the only way that we can get a sum of 6, given that the first die is even, we can get it this way. First die is 4, second die is 2. Or we can get it this way. The first die is 2, the second die is 4. So there's only 2 ways that we can do this. And now the total number of outcomes given that E1 is true. Total number of outcomes given that the first die is even. Okay. This whole row, the first die is even. This is 6 outcomes. This whole row, the first die is even. That's 6 more outcomes. This whole row, the first die is even. That's 6 more rows. So 6 plus 6 plus 6 equals 18 outcomes where the first die is even. And we sort of expect that. There are 36 possibilities. Half of them have the first die being odd, the other half have the first die being even. So the probability of getting a sum equals 6, given that the first die is even, is 2 out of 18. Let's remember that for the second part of this problem. Determine the probability that the sum of the dice totals 6, and the first die is an even number. E1 and E2 are the same in this exercise, but we're computing something different. We're computing the probability that the sum of the dice totals 6, and the first die is an even number. So we are computing the probability. The first die is an even number, and the second is that the sum of the dice totals 6. And are these events independent? No, they're not. There are 5 ways that we can get a 6, but only 2 of them happen when the first die is an even number. So we'll use our conditional probability formula, which is probability of E1 times the probability of E2 given E1, which we computed just before this. Probability the first dice is even, E1. Here the first die is 2. Here the first die is 4. Here the first die is 6. Looking exclusively at the first die, there's 6 outcomes. The first die can either be a 1, 2, 3, 4, 5, or 6. So there are 6 outcomes. Yeah, let me compute that. Probability of E1 number of outcomes resulting in E1 over total outcomes. And we're just restricting this to a single die, the first die. If we toss the first die, there are 6 total outcomes. We either get 1, 2, 3, 4, 5, or 6. And if we toss the first die, we can get an even number 3 ways, 2, 4, or 6. So there are 3 outcomes that result in E1. So the number of outcomes resulting in E1 is 1/2. I'm sorry. The probability of E1 is 1/2. The probability of E2 given E1, we computed that in the last exercise. And that was 2/18. probability of E1 and E2 is going to be 1/18. In our text, our authors have an alternative formula that may prove helpful. We have the conditional probability of E1 and E2 being equal to probability of E1 times the probability of E2 given E1. And if we divide both sides by the probability of E1, this is what we get. And if we take this equation and just switch sides, this is what we get. A formula for the probability of E2 given E1. And if we write this in terms of number of outcomes yielding E1 and E2 divided by total number of outcomes and number of outcomes yielding E1 divided by total number of outcomes, and do some canceling, this formula reduces to this formula. Now we're going to do some probability exercises in which we want to compute the probability of a certain event given that another event has occurred. Sometimes this will be a nice formula to use. Sometimes this will be a nice formula to use. And we should probably know both of them. Let's go back to our dice. This is the sample space of 2 dice being tossed. This row represents the results when we toss the first die. This row represents what we get when we toss the second die. So this represents first die equal 2, second die equal 1. This represents first die equal 2, second die equal 2. This represents first die equal 2, second die equal 3, and so forth. Let's use the formula that we just were exposed to or introduced to do this exercise. A pair of dice is tossed. Compute the probability that the sum of the dice will equal 3 if the first die is a 3. So we'll let E1 be the event that the first die equals 3, and E2 will be the event that the sum of the dice equals 3. And we want the probability that the sum, E2, equals 3, given that the first die is 3. We can do this without using the formula. We can just say, wait a minute now. This is the row where the first die is equal to 3. And I don't see any sums here that are equal to 3. The probability is 0. And that's correct. For the sake of gaining facility using this formula, let's use the formula. And what we get is the number of ways that E1 and E2 can occur over the number of ways that E1 can occur. And E1 is the event that the first die is a 3. In this table, we have 6 rows and 6 columns, 36 total outcomes. And of those 36 outcomes, how many of those result in the first die equaling 3? 1, 2, 3, 4, 5, 6. So the number of ways or the number of outcomes resulting in E1 is 6. Now, what about the number of ways in which we get E1 and E2? How many ways can the first die equal 3 and the sum of the two dice equal 3? If the first die equals a 3, then the sum either has to be 4, 5, 6, 7, 8, 9. Did we see 3 anywhere in this row? No. So the number of ways that E1 and E2 can both happen is 0. So the probability of E2 occurring, the probability that the sum will be 3, given that the first die, E1, is 3, equals 0. Let's do some more exercising using this formula. Okay, let's look at this exercise. A pair of dice is tossed. Compute the probability that the sum of the dice will equal an even number if the first die is a 2. We can reword this in conditional probability lingo. They say compute the probability that the sum of the dice will equal an even number if the first die is a 2. In conditional probability lingo, what they're really saying is compute the probability that the sum of the dice will equal an even number given that the first die is a 2. So what we had worded here is if, that's the same thing as given that the first die is a 2. So E1, we'll let that be first die is a 2. E2, the sum of the dice equals an even number. And what we want is the probability of E2, the sum of the dice is even, given that the first die is a 2, E1. And let's write down our formula. Number of ways that E1 and E2 can both happen together over the number of ways that E1 can happen. E1 and E2. First die is a 2 and the sum of the dice is even. Okay. This row is the set of all outcomes. Let me get my pointer here. This row is the sum of all, this row is the set of all outcomes in which the first die is a 2. So let's see. This is even. this is even, this is even. The outcomes that I've circled are the outcomes in which E1 is true, the first die is a 2, and E2 is true also, the sum of the dice is even. Note that there are just 3 ways that E1 and E2 can both happen. And that is, the first die is a 2, the second die is a 2. We get something even. The first die is a 2, the second die is a 4. We get an even sum. The first die is a 2, the second die is a 6. We get something even. So the number of ways in which E1 and E2 are both true, 3. The number of outcomes that result in E1, this row is the set of all outcomes that result in E1. E1 is getting a 2 on the first die. If we get a 2 on the first die, then either we get a 3, 4, 5, 6, 7, 8 total. Or another way of looking at this, if we get an E2 on the first die, then the other possibilities are we get a 1, 2, 3, 4, 5, or 6 on the second die. But this row of outcomes is the set of all outcomes in which E1 is true. In other words, set of all outcomes in which the first die is a 2. And there are 6 of them. So the probability of E2 given E1 is 1/2. A dice problem again. A pair of dice is tossed. Compute the probability that the sum of the dice is a 7 or an 11 if the first die is a 5. And again, let me rewrite that in probability lingo. Instead of saying if, let me say given that the first die is a 5. That being the case, we'll let this thing be our E1, and this thing, the sum of the dice is a 7 or an 11. We'll let that be our E2. So E1, first die is a 5. E2, the sum of the dice is a 7 or an 11. And we want the probability that the sum of the dice is a 7 or an 11. That is, we want the probability of E2 given that the first die is a 5, E1. That's what we want. And according to our alternative formula, this is going to be the number of ways in which E1 and E2 are true over the number of ways in which E1 is true. for a number of outcomes resulting in both E1 and E2 over the number of outcomes resulting in E1. Okay, number of outcomes resulting in E1 and E2. First die is a 5, and the sum is a 7 or an 11. This row is the set of outcomes in which the first die is a 5. Okay? First die is a 5. And maybe I should end my loop here. All of these outcomes that are circled are outcomes in which the first die is a 5, and that's E1. How many of these outcomes are there? 1, 2, 3, 4, 5, 6. Okay. So the number of ways E1 can happen, that is, first die is a 5, is 6. What about the number of ways that E1 and E2 can happen? The first die is a 5, and the sum of the dice is 7 or 11. Well, since we are insisting that E1 and E2 both happen, in other words, the first die is a 5 and the sum is a 7 or an 11, we're only going to look in the row that has outcomes in which the first die is a 5, E1. Now, of the outcomes in this row, which ones give us a 7 or an 11? This one does, and this one. So there's just two outcomes that give 7 or an 11 if the first die is a 5. If E1 is true, the first die is a 5, there are only two outcomes that will give us 7 or an 11. Now, why did that turn out to be 7? I said there are two outcomes, 7 and 11, in which E1 and E2 are true. There, do we like that better? I sure do. So the probability of E2 given E1 is 1/3. That's the probability that the sum of the dice is a 7 or an 11, given that the first die is a 5.